So starting with a very simple rigid link system, we have a link of length L. It happens to be pinned at the bottom. The top support has some flexibility. We're going to model that with a spring, a translational spring with stiffness K, and a load P is applied in compression at the top of the link. So the system is determinate in terms of support forces 2, 1, although we have some flexibility. So what we're going to do is explore equilibrium in the deformed configuration. So we're going to take that link and we're going to perturb it. We're going to move it, displace it, and I'm going to move it in amount theta, which then causes a displacement at the top, theta L. So let's go ahead and look at what the free body diagram looks like. There's the perturbed system. I'm going to go ahead and label that angle theta. That puts then at the top a displacement theta L. Again, notice these perturbations are very small, but they're drawn large so that we can see them. So at the top, force-wise, we've got the applied external force P. The pin, we'd have an F1 and an F2. Those would be the pin forces. And then activated would be a force in the spring, which we've cut. So we now see the force in the spring that was supporting the top. And so there's the free body diagram in the displaced configuration. So notice that force in the spring is a restoring force. It's going to be equal to the stiffness times the stretch in the spring. Initially, there is no stretch in the spring. It has no force in it. So it's going to be K times the stretch, which would be sitting there as theta times L. So we'll do equilibrium in the deformed configuration, and we can avoid solving for these forces down here by just spinning a moment. So let's go ahead and do that. Spin a moment at the bottom, and when we do that, that's got to equal 0. So the equation that we end up with is minus P times theta L, the applied external load. Force in the spring would be acting in the positive direction, so we'd have force in the spring, and it has a lever arm of L, and adding those together has to equal 0. So let's work the equilibrium equation a little bit, and so minus P theta L plus the force in the spring, which is K theta L times L, has to equal 0. We can factor out theta L. We get minus P plus KL has to equal 0. So our conclusion would be that either theta equals L, or the other term has to equal L minus P plus KL equals 0, which would tell us that P equals KL. So talking a little bit more, this theta equals 0 really would be the trivial solution back in calculus class. Here in engineering, it really be impossible that this structure would have theta equals 0, exactly 0 for all time. So really, this is the conclusion that we come up with. This is called the critical load. So we end up with the critical load is equal to K times L. So as long as that applied load is less than P critical, then we have something stable. If P exceeds P critical, then we are unstable.